Hey everyone, and welcome back to the Explainer. Today, we are decoding an absolute breakthrough in computational materials science. We're going to look at how a team of researchers managed to drastically reduce simulation times for short fiber-reinforced composites. And the crazy part is, they did it without sacrificing a single drop of accuracy. Let's get right into it.
To really ground our discussion today, we're pulling our insights straight from the source. This is the paper Coupled Multiscale Modeling for Short Fiber Composites, published in the highly prestigious journal Composites Part A back in 2022. Authored by Castricum and an incredible team of colleagues, this paper lays down a rigorous technical foundation for a highly efficient new modeling framework. Our goal today? To unpack their incredibly smart mathematical work step by step.
All right, here's our roadmap for the Explainer. We'll start with the multiscale challenge and the micromechanical model. Then we'll look at how they coupled the macro and micro scales. After that, we'll explore exactly how they boosted efficiency, and then we'll wrap the whole thing up with real-world validation and simulating actual physical structures.
Section 1. The Multiscale Challenge, Predicting Nonlinear Elasto-Plastic Behavior.
So why is predicting the mechanical behavior of these composites so notoriously difficult in the first place? Well, it all really comes down to the manufacturing. As the authors themselves point out, manufacturing processes like injection molding create complex, highly varied fiber orientations throughout a single part. Because the fibers aren't just neatly lined up in one uniform direction, you can't just slap a simple mathematical equation on it and call it a day. You have to account for local variations everywhere, and traditionally, that requires a truly immense amount of computational power.
Section 2. The micromechanical model. Zooming into the fibers.
To solve this massive macroscopic problem, we actually need to zoom all the way down to the microscopic level. What we're looking at is the researchers' two-step orientation averaging approach. Moving from left to right, step 1 defines a single unit cell, basically just one fiber surrounded by its matrix material, and obtains its baseline properties. Then, step 2 takes those properties and averages them out based on how the fibers are actually oriented out there in the bulk material. This gives you the fully homogenized composite properties. Now, before you can do all that averaging, you have to lay down some ground rules for how those unit cells behave inside the larger composite. The authors clearly define 3 different global-local interaction assumptions here. First up is Voigt, which assumes uniform strain across all cells, effectively giving us an upper bound for stiffness. Second is Rice, which assumes uniform stress, giving us the lower bound. And third is the self-consistent assumption. This one is super interesting because it treats each unit cell as if it's embedded in an equivalent homogeneous medium. It implicitly accounts for fibers interacting with each other, which makes it highly realistic, but as you might guess, incredibly mathematically complex.
Section 3. Coupling macro and micro. Bridging the scales.
Okay, so we have our micro rules, but how do the macroscopic structure and those microscopic unit cells actually talk to each other? What's really fascinating here is the flow of information. Notice the dashed arrows illustrating this nested framework. Basically, macroscopic strain from the large structure is passed down to the micro level. The micro level then steps in, does all the heavy lifting to calculate the local behavior, and then passes the homogenized stress right back up to the macro level.
To be totally precise, this all happens in a very specific 4-step loop at every single integration point in the finite element mesh. Step 1, the finite element analysis calculates the macro strain. Step 2, the micromodel uses our interaction assumptions to determine local unit cell strains. Step 3, a surrogate model calculates the unit cell stress. And Step 4, the homogenized macro stress is averaged out and returned to the finite element model. Now remember, this loop happens thousands of times using an explicit time-stepping algorithm. You can probably imagine how incredibly expensive this gets computationally.
Section 4. Boosting efficiency, the mathematical optimization.
This is where things get really good. This is where the researchers solve the massive computational bottleneck of that nested loop we just talked about. The crucial game changer here is a shift in how the math is integrated. Look at the stark contrast. Traditionally, engineers brute-forced this with trapezoidal integration, evaluating literally thousands of random computationally heavy points on a sphere, just to average out the fiber orientations. Castricum and the team said no to that, and replaced it with the Voigt and Lebedev quadrature schemes. Instead of thousands of random points, these optimized schemes evaluate a much smaller number of highly symmetric, strategically placed points. It's working smarter, not harder.
And the results? They are stunning. When using the old method with thousands of random fibers, the calculation time was huge. But when they swapped to the optimized Voigt schemes, the calculation time was absolutely slashed.
For the Voigt and Roos interactions, the time required essentially drops all the way to 0. It's almost entirely wiped out.
But you might be wondering, what about that complex, self-consistent interaction we talked about earlier? That one requires calculating the notoriously heavy Eshelby tensor. Well, by utilizing the Lebedev 974-point scheme, they managed to cut that calculation time in half compared to traditional numerical integration. A 50% reduction on the hardest math on the model is a massive win.
Section 5. Real-world validation. Proving the math works.
Of course, getting the simulation to run incredibly fast is totally useless if the results are wrong, right? But check out these stress-strain curves. The heavy traditional reference case and the new lighter Bézant schemes overlap almost perfectly. You can barely see the difference. But more importantly, as the researchers proved in the paper, these fast mathematical predictions align beautifully with actual physical experimental lab results. The math isn't just fast, it is entirely accurate.
Section 6. Simulating real structures, the macro application.
Let's zoom all the way back out and actually apply this model to a physical object. Here we're seeing how the model handles a real, injection-molded dog bone part. Just like we discussed at the very beginning, manufacturing creates varying orientations, but the model maps this seamlessly. It easily accommodates aligned fibers at the skin layer and random orientations right in the core. And because of that, it flawlessly predicts stress concentrations exactly where the fibers align with the load. To really cement the true value of the framework built by Castricum and colleagues, just look at these final performance metrics. Overall, computational efficiency improved by 99% for the Voigt interaction, 48.6% for the highly complex self-consistent interaction, and 98.9% for the Roos interaction. They didn't just speed up the bottleneck, they essentially solved it.
If you want to explore more incredible work from this research team, I highly encourage you to go visit materialslab.org, which is the online home for the Mechanics and Physics of Materials Research Group. As we wrap up this explainer, I want to leave you with a final thought. If simply swapping to smarter geometric integration schemes can eliminate 99% of computational time in this specific instance, what other massive computational bottlenecks in engineering are just sitting there waiting to be solved simply by looking at the math from a slightly different angle? Keep learning, keep questioning, and I'll see you next time.